Seismic PE Prep number 16 coming at you right now. It's all things portal frames today and how you can apply that in potentially your next design. Force F is acting on the frame shown. The framing system is equally spaced between columns. Applying the portal frame method of frame analyses, what should the distribution shear be at column 2? You are likely to encounter two different frame analysis methods on the Seismic PE exam. Portal frame method like we have here today, and cantilever frame method that we'll do in another video. Commonly in the professional field, we replace both of these methods with analytical software, something like eTabs, SAP 2000, plenty of other things in between. However, you should always come back to the basic principles and understand how to do both of these frame analysis methods by hand. For starters, it's a fantastic way to spot check your computer model to make sure that it's doing the things that you actually want it to do. That is a big thing in the structural engineering world, in the professional world, that your boss, your principal, your project manager is going to want to see you do, so that we're not just trusting these black box computer models. Today's question is pretty straightforward and we can answer it, and I think you might have already answered it in the past 30 seconds and moved on to the next problem. However, I'm going to start by writing down some notes that I took as I studied for the SE exam to really in-depth understand the characteristics behind portal frame method. So let's jot those down. I think they'll be beneficial for you, and then let's knock out this problem. Let's go. Let's call it a portal frame cheat sheet, if you will. You can use the portal frame method for low-rise structure analysis. I'm not sure where the cutoff actually happens, 3, 4, 5, 6, somewhere in there. I'd have to double check on that. And then there's 4 assumptions that are made when we're using this method for analysis. 1, an inflection point is located at each column's mid-height. An inflection point is also located at each beam's mid-span. 3, this is a big one here. This is what we're going to be using today to solve the problem. Horizontal shear is divided among columns in the ratio of 1 part at exterior columns and 2 parts at interior columns. And then 4, members have the same cross-sectional area and stiffness. So you can see how this is a simplified approach to doing a frame analysis. A lot of things have to be boiled down and made into a simplistic type of structure. And we know that nowadays, especially for 3, 4, 5-story structures, let's call it a steel frame structure, you're not always going to be able to get away with just doing the same beam, same column, same frame everywhere. You're going to have some unique geometries happening, some architectural features and flares that you want to pull off some cool parts of your space. So this can't always be a catch-all to do all sorts of different custom buildings. But again, it's a great boiled down approach to be making sure that you're based in reality, the numbers that you're seeing in your analytical model, in your software are correct, and you can be comfortable to move forward with them. All right, now we have all of our notes, but let's visualize this with a figure. First, we're doing a fixed condition, and then we'll go over a pinned base condition. And right now I'm drawing in all of our inflection points. So mid-span of all beams and mid-height of all columns. I did forget to mention that typically the heights of your frames are less than the widths of your frames, or the inverse of that is your frames are wider than they are tall for this type of analysis. The exterior columns are 1/2 the amount of the interior columns, or again, the inverse is the interior columns are 2 times as much shear as the exterior columns. How can we convey that? You can do V for shear, you can do H for horizontal reaction, whatever you would like, as long as you keep it straight in your head. And this is applicable for as many interior columns as you have in your frame line. You could have 10, you could have 2, you could have 1, you could have 6. It would be 2H, 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 and then you just have your 2 exterior columns being HH, okay? And now, if we were to start to break this frame down and really start to do the analyses, what would I do first? Well, we know that we have, at each one of these inflection points, we have moment equal to 0, because all of these joints in our frame are all assumed to be moment connection. And so all of our moment is going to be located at our joints. Having the same stiffness and the same members for every single one of our members in our frame, our moment diagram could be something that we can sketch out. It's equally stiff at the top as it is at the bottom, so the load distribution is going to move to the 2 stiffest portions of the frame, or of the column in this matter, and so your moments accumulate at both extreme ends, meeting in the middle where it will be 0. This is the same for all of our beams as well. And so on and so on and so on. You could draw these all over the place on your frame. Now, the next step that you take when you're doing this analysis is you cut through the story that you're trying to analyze, or the members that you're trying to get forces for, through the inflection point of the story in question. So if we were analyzing starting at the top, we would cut through the midpoint or at the inflection points of the second story columns. It would be, the story height would be, if I call it L, would now be L over 2 because it's 1/2 of the story. And you know that your moments diagrams look like that. The beams still look like that. If I'm drawing them the right direction, if I'm drawing them the opposite direction, apologies for that. You have your story force, and then you have your same rules for the columns. You have H, 2H, 2H, H, and you have some story force. I'm just going to call it F. And then from here, you can just start doing statics to start figuring out what your shear demands are at each one of these columns, and then from there you can back that out to find the moments at each one of the column ends, and then from there you start to populate and give and define the amount of moment in your moment diagrams and the amount of shear in your shear diagrams, and then you can go from that point and design your frame and design your connections, and you're off to the races. The only thing that changes when you have a pinned base condition is like shown here. So your shear distribution to your column still remains the same principle. However, your inflection point changes. It's no longer for the bottom story or the bottom columns. It is not at the mid-height of the column. It's now dragged all the way down to the base. And that's because, as we all know, no moment can translate through a pin connection. The inflection moves to the bottom, and 100% of the moment is now at the top of the column. Your moment diagram now looks like that. And you now need to cut through the story in question. If you're looking down at the base, well, you need to cut through the inflection point. So you literally just cut down at the base level, not through the mid-height. And then you go through, you run some statics, and you get your moments and your shears throughout your frame that way. All right, that's enough. Let's solve this thing. So column 2, shear, we know is an interior column. So it gets that 2 times the shear as the exterior column. There are a couple of ways you can just internally process this. You can kind of just, instead of H, you can take it in terms of F, because at the end of the day, all 4 of these need to add together to equal F. That way you balance your horizontal statics. And so, you could do some fractions in your head and say, all right, well, let's see. I believe this would spit out to be 1/3 of F, and that would equal column 3, so that would also be 1/3 of F. So that's 2/3 of F, and then 1/2 of 1/3 is 1/6. So 1/6 of F and 1/6 of F. 1/6 plus 1/6 is another third. That makes 3/3, which makes 1. So that would equal F. Instead of doing it in variables, which I never like to do, I like numbers, you can instead turn F into just a unit of 1. Now, if you have 1, you could, it's getting messy here, but you can just stick with the nomenclature that we had. So H, 2H, 2H, H, call them F if you want. But now, it's just a little equation that you need to balance. F equals H plus 2H plus 2H plus H, and then plug in. So 1 equals H plus 2H. You sum all the H's together. 1 equals 2, 4, 5, 6. H equals 1/6. Aha. And since we're looking for column 2, which we denoted as 2H, it means that 2H is equal to 2 times 1/6, which is 2/6, which reduced is 1/3. So 1/3, and since F equals 1, is just F over 3. So I would say our final answer is D, 1/3 of the story force for this frame analysis, under the Porto frame analysis method. I know it was really quick, but I wanted to get these notes to you and that you can digest them to make sure that you're applying this method appropriately, what your constraints are, what your limitations are. I think that is by far just as important as being able to plug and chug and get a solution. I get maybe not for the exam, but to build your engineering ability when this becomes, more complex than just a 6-minute solution with 4, multiple choice answers. Let me know in the comments down below if I was all over the place, if you want more of this, if you want less of this. Thanks for liking. Thanks for subscribing. Tune in for any structural engineering detailing that you want to see live. I'm doing it Thursdays at 6 p.m. We had our first session. It was really great. So that sounds good to you. Jump on in during your studies, after your studies, when you're taking a break, whatever. But I appreciate all of you. This is Rich with Team Kestävä. Peace.